Okay, good morning, everyone. Welcome to the last session of Cloud Academy. Just a few reminders before we start. You are kindly asked to vacate your room by 10 a.m. this morning. Probably all of you have done already, so thank you. Another reminder is that if you need to pay for any cold drinks here, please do so. And I think that's probably all in terms of logistics. So it's my pleasure to welcome the first speaker today, Connie Jaeger, who will tell us about laboratory studies of dust condensation.
Thank you. Yeah, good morning, everybody. Yeah, I will speak about laboratory studies of dust condensation, and I have to say at the beginning of my talk that I'm rather an alien in this group because I'm normally working on dust condensation in other environments. So we are mainly interested in in condensation of cosmic dust in different environments. So especially, for example, in evolved stars, where we have the major dust producers. So I mean, dust is produced in HEB stars or in more massive stars, and also in supernovae. These are our fields of research. But I also have to say that there are very dangerous places for dust in the universe. So dust can efficiently be destroyed in the stellar medium due to different processes like shocks here, the diffuse in the stellar medium, or erosion in molecular clouds, and evaporation in protoplanetary disks. So in order to get a balance between, let's say, dust destruction and formation, one needs to have dust condensation also in this area at very different conditions compared to these ones here. So we are interested in, let's say, high temperature dust condensation and also low temperature dust condensation. The key questions we want to address in our research are the following. So, of course, first the general one, which is, what are the precursors, the intermediates, the chemical pathways of dust condensation. This is very important to know because the chemical pathways determine the composition of the material and the structure of the condensed material, and the composition and the structure determines, of course, also the spectral properties of the grains. So this is a very important question. And another important question, which is often addressed in our studies, is what are the nucleation seeds? And here we are still at the very beginning because nobody knows exactly yet what are nucleation seeds in different condensation processes. Minor problems we have addressed in former studies are, for example, can we condense only pure magnesium ion silicates, or can we also condense mixed magnesium ion silicates, in contrast to the claim by Riedmeier et al. 1999, who said that only pure components here along these lines can be formed, and only later the material reacts and form mixed silicates. So another big question is, do we condense amorphous or crystalline material? For carbonaceous material, the question is fullerenes versus PEHs. So what are the precursors? What are the main subunits or building blocks of carbon grains? And also, for example, another important question, diamond formation. So this is also not yet understood. Okay, so apart from the laboratory approach, there's of course the theoretical one. So here's a nice graph shown, presented by Geil, 2011. So this is a normal condensation calculation based on chemical equilibrium and nucleation theory. And of course, it does not reflect the conditions in HEB stars, because in HEB stars, during the condensation, we will never reach the thermodynamic equilibrium. But of course, it helps to interpret what we see and to, let's say, to understand at least a part of the process. So we can get information about condensation sequences, which can be shown here. Here we see the stability limits for the different materials. This is a graph showing the condensed phases in for a cosmic standard element mixture in oxygen-rich outflow. So you see corundum, gyelenite, spinel, diopside, forsterite, and satite is formed at different temperatures. Here the dashed line represents stationary outflow of the in the star. So condensation, when we want to do something in the laboratory, we have to know which kind of conditions we have to realize, and this is something which is difficult to obtain. So generally pressure, temperature conditions or diagrams are difficult to obtain because these are things which are based on model assumptions. So that means one needs to know exactly the velocity, the mass loss, the density, and so on. I mean, there are a lot of uncertain parameters which go into these molecules. However, there are, let's say, some kind of rough estimates. For example, Lederer et al. 2006 presented two pressure-temperature diagrams where you can see, for example, for a warmer star at 4000 K, you see a pressure between 0.8 and 1 times 10 to minus 3 millibar in this condensation zone. Or for a warmer, for a colder star, the pressure is even lower, between 0.01 and 10 to minus 5 millibar. So, however, I mean, it's not so easy, which can be seen here in this scheme presented by Gobrecht et al. 2016. They also try to theoretically approach or understand the condensation of the material in such evolved circumstellar shells of evolved stars. And what has to be said here is that we have to consider also thermal pulses in such stars. So these thermal pulses are continuously changing the composition of the circumstellar shell. This is one thing. But also, of course, thermal pulses increase the temperature and also the density of the material for some time. And so it has already been observed that dust production is a kind of, let's say, pulsed process. So, and all the chemistry which is really taking place here in this zone is based on a non-thermal equilibrium shock chemistry, and one has to consider always a kind of continuous destruction condensation processes. So it's a very complicated process, and parameters which can be used in the laboratory to let's say design experiments are difficult to obtain. So anyway, I mean, all the pressure ranges we have seen here in these slides are a little bit low compared to what we can do in the laboratory. So of course, when we want to study condensation in the laboratory, we have to scale up the pressure. So at least 1 order of magnitude, sometimes also 2 orders. So it's something we have to do. Otherwise, we have to design very large instruments, devices to condense, to homogeneously condense the material. So coming to the experiments we are doing in Jena. So we have 2 types of condensation experiments. So this is laser pyrolysis. It's a very useful approach. So the characteristics of laser pyrolysis is that you start with gaseous precursors. So for example, if you produce carbonaceous condensates, you start with hydrocarbons like acetylene, ethylene, benzene, or you can also use methane. So the gases are introduced into the chamber through the inner tube here, and they are confined by a so-called confinement or quenching gas, so which is normally a rare gas, argon or helium in the most cases. So the perpendicular to the beam of the gas, we have a CO2 laser which dissociates the gas here. And of course, due to the collisions with the quenching gas, we get the supersaturation here in this zone and homogeneously condensed particles here. We can finally deposit the particles in a filter, or we can extract them very efficiently by adiabatic processes like adiabatic extraction through a nozzle and a skimmer. The condensation zone here looks like this. It's a small flame, and condensation takes place in the cooler part here of this flame. This is a method which can be used not only for carbon but also for silicates normally, but the requirement is that you have a gaseous precursor. So we have already used it to produce iron silicates, but it's difficult for magnesium because there is no gaseous precursors for magnesium. So the the temperature here in the condensation zone, this is one important thing we can a little bit, let's say, influence by choosing two different types of lasers. So if we use a pulsed one, then we have a very high power density here in the dissociation condensation zone, which is shown here. It's between 10 to 7 to 10 to 9 watt per square centimeter, and you can correlate this to a temperature, and this means we achieve temperatures which are larger than 3500 K. This is, but I have to say, this is the vibrational temperature of a gas molecule. So, sorry, I forgot. If we use a continuously working laser, the density here, the power density is much lower. So, and we reach only temperature lower than 1700 K, so up to 800 or even less. So the other method we can apply in the laboratory is laser ablation. This is in contrast to laser pyrolysis. I mean, here we use a solid target. We evaporate again with a laser, produce, let's say, atoms and small species. You can see here the target is rotating, and the laser hits the target, evaporates the material, a kind of plume is formed here. So the target is here. So, and this is the ablation chamber. The pressure in the ablation chamber is between, let's say, 1 up to 15 millibar. So normally we work up to, let's say, 4 or 5 millibar, very low pressure. So here, in this laser ablation, we can really achieve homogeneous nucleation of silicates or carbonaceous materials, depending on what kind of target we use here for the condensation. And for carbon, we use, of course, graphite, and then we condense in a helium or helium hydrogen atmosphere. Hydrogen is a reactive gas here and introduces hydrogen into the carbon structure. And if we want to produce something like silicates, we start either with a silicate and condense in a helium atmosphere, or we use metallic targets and condense in an atmosphere which is containing oxygen. And of course, here by this process, we can also a little bit control, let's say, the oxygen content in the final silicate. So we can, of course, work in a very oxygen-rich atmosphere. Or we can go to, let's say, very deficient atmosphere, so that we can a little bit also influence the composition of the silicates. For example, we can produce oxygen deficient silicates which might contain, let's say, metallic iron components, and these kind of things are possible in this setup. Before I come to the results of the condensation experiments, I would like to say something on silicate structures. And so during the last 2 days when I came to this workshop, I realized that silicates play a very important role, probably a bigger role than the carbonaceous condensates, even though we have yesterday heard that also soot is produced in the atmosphere of Titan. Yeah, anyway, I will a little bit focus on the silicates here in my talk. So, and before I come to the results, a few words to the structures. So, pyroxene and oleines, these are the crystalline materials. For the crystalline materials, we have a very definite structure. So, for the stoichiometry here given, we need to have chains of SiO4 tetrahedra, and in between these chains we have magnesium or iron, cut ions. And the pyroxenes form a solid solution series, so you can easily replace magnesium by iron, even though there are some slight changes in the oxygen metal distances. So olivine, again characterized by SiO4 tetrahedra, and but due to the stoichiometry, we cannot have bridges, oxygen bridges between the tetrahedra, so they are isolated, and in between we have the magnesium or iron. So if we go to something very amorphous, so I would like to show you two snapshots here. This is based on a calculation of a silicate structure. This is a pyroxene material, this is olivine material, and I have to say that an amorphous structure is not well defined. So even though so everyone speaks of amorphous silicates, but this is not only one, let's say, compound. It can be a lot of different compounds with slightly different structures and also slightly different spectral properties. And this is shown here. You can see in this snapshot how the SiO4 tetrahedra are condensed in such an amorphous structure. You can imagine that in, let's say, 5 seconds later, it could be completely different. And also here you can see that there are differences in the coordination spheres, for example, for magnesium or for iron. Normally you have a 6-fold coordination here and here, but you have also 5-fold or 4-fold coordination in the amorphous material, additional oxygen somewhere. So this is something you have to keep in mind when you look at optical constants or spectral data of silicates, and they differ from time to time. So what did we produce when we studied the condensation of silicates? So first I have to say we never produced crystalline silicates, never ever. So if you produce these silicates by homogeneous nucleation, you really start with something amorphous. So you can see here, this is an electron microscope image, a high resolution electron microscope image. You see here the primary particles. They already started to condense together. It's a little bit difficult, but here you can see it. So, and they form up agglomerates and, let's say, fluffy structures of the dust grains. And what the second thing what I can say here is that we, of course, produced magnesium iron silicates, mixed systems, not only the pure ones. So this is something which is probably, I mean, this statement of Riedmeier was probably due to some experimental difficulties. So if we look here at the spectral data of the condensates, you can see the typical spectral data here. So this is the pyroxene, this is the olivine here. The typical bands here are the SiO stretching band at 10 micrometer, and the deformation or bending of SiO here at 20, at around 20. So here this is a little bit water from the pellet we had to produce, so this is kind of artificial material here. So if you go from a magnesium silicate to with a pyroxene composition to olivine, then you see a shift of this band to longer wavelengths here, and this band shifts to smaller wavelengths a little bit. And this is also what we would expect. I will say something about this in the next slide. So, however, I want also to stress something what is shown here. You can also produce something amorphous, but which has not the typical, let's say, band structure like the normal pyroxenes and olivines. So this is a material which is amorphous but has some SiH bonds inside. So you can see here the SiH band here at about 4.6 micrometer. And due to this SiH band, you can have a slight shift of this SiOH stretching band, and then you have the appearance of the second band, and it looks a little bit like a crystalline material, but it's amorphous. So the something on the, let's say, on the spectral tendencies we can see in the silicates. This is shown here. So the absorption spectra of differently produced silicates. These are produced by salt shale, but these are all also amorphous and very similar to what we produce in the laser ablation system. You can see that when you change the composition from, let's say, 1 Mg 0.7 SiO 2.7, which is the first one here, so the color changed. And you go to olivine or more as a non-stoichiometric olivine type material, you shift the 10 micrometer band to the longer wavelength. This is expected because you change the polymerization degree of the SiO4 tetraeder, and if you reduce the polymerization degree, you get this shift. So, and the other band shifts to the shorter wavelengths a little bit. However, this is not so clear. I mean, this is a very clear trend if you look only at the magnesium silicates. If you introduce iron, then you get a longer distance between the metal and the oxygen, and then you also shift a little bit the bands to longer wavelengths. This is well seen in the crystalline material because we have narrow bands here, and we can clearly see, or more clearly see, the shifts. But this is of course also a tendency you would also see in a amorphous material. So you have to keep in mind that the polymerization degree, but also the introduction of iron, may shift the bands. So, and also of course shape effects. Here I can show you something which was studied by Tamanay et al. 2006. So she tried to measure the influence of irregular and ellipsoidal shapes on the profiles of crystalline silicates, and you see that there are changes due to the shapes of the material, and also of course the sizes matters. So if you increase the size of the grains from the Rayleigh case to larger particles, you also broaden and shift. So these are effects which are very important to know if you want to interpret your spectra concerning, let's say, the type of the silicate you have produced. Another problem I wanted to show here for the moment is that also spectral properties are temperature dependent. This was clearly shown by Dimick et al. And this is something which is also very important if you consider, for example, long wavelength spectral properties of silicates or of oxides, for example. The problem is if you decrease the temperature, then you get a decrease here in the absorption, and also a change in the slope of the curve here. So, and very interestingly, that's why I wanted to show you is that if you compare these measurements to the astrosilicates derived by Drain, for example, or the silicates based on this TEMIS model, then you see there are really big differences between the laboratory studies and the theoretical, let's say, approaches to the spectral data of the material. So keep this in mind. There could be large differences. So this is a kind of let's say, outcome from our, let's say, condensation and spectral measurements. So this is a nice fit of emission of oxygen-rich binary star presented by Gielen et al. 2011. And you can see here, after the subtraction of a continuum, you can see the emission bands which has a certain structure, and you can fit these bands with an amorphous part or amorphous material, amorphous olivine and pyroxene, iron containing with different sizes. And in order to get the structure here, then you have to add some forsterite and anstatite and silicate. So you can really see that this kind of circumstellar shell is composed of these, let's say, major components. A few last words to something which could also be of interest. So we also studied the condensation of carbonaceous materials. So, and here I just want to compare what we have seen when we compare the homogeneous nucleation at different temperatures. So if we condense the carbonaceous material at temperatures higher than 3500 K, then we condense fullerene-like material, and we can see that a condensation process based on chain-like precursors takes place. So the precursors are chains which are growing and then start to branch, and then they react together, and the first rings are formed, and later on there is a restructuring, and fullerene structures, fullerene fragment structures can be formed, and they build up these kind of materials. If you go to lower temperature, lower than 1700, you can see that only PEHs play a big role. Here we have probably nucleation seeds which are, let's say, made of clusters of PEHs. So, and the grains you can see here are made of really large and flat PEHs. And in addition to the grains, in such a low temperature condensation, we get always a lot of PEHs. And if you look at these condensates much more in detail, so for example with high resolution mass spectrometry, which is shown here, then you can see that you produce really a very huge variety of different pH material. You produce really every mass and every isomer you can imagine, up to masses of, let's say, 3000 or even higher Dalton. What I mean, the sizes of these pHs are really varying from very small up to very large. So this is something, I mean, here we can really exclude the fullerene structures, and here on this side we can exclude the pHs. So from the studies with the special mass from the special mass spectrometer studies, here we used MALDI combined with time of flight mass spectrometry. We can really exclude fullerenes here. So I'm a bit late. Okay, thank you. Okay, then a few words only to the, let's say, the second part of experiments we are working on at the moment. So as I said, we are also interested on the low temperature condensation. Low temperature means at conditions in the interstellar medium, for example, in the diffuse interstellar medium or in the molecular clouds. So that means very low temperatures and low densities. So, and this is the kind of idea what is, what the people have about interstellar dust grain in this environment. So at least in more dense environments, you have surviving dust grains on which, on the surface of these grains, gases agreed and form a kind of ice layer. The major part of these ice layers is water, but also CO, CO2, methane, methanol, and so on. And then you can trigger a very rich chemistry here in this ice layer by UV irradiation, electron irradiation, cosmic rays, and so on, just by high energy processes. And I mean, this is the kind of, let's say, general idea how the complex organic molecules are formed. However, what is also known that shock waves destroy the dust grains which were formerly produced in HEB stars. And so also refractory species should be deposited or accreted on in these ice shells, so like I have shown here. So apart from the normal gases, you have probably also something like FeO, FeOH, something like CH, CHO, SiH, and so on. Refractory species which can somehow contribute to the condensation of silicate or carbonaceous material. And we are really studying this process in the laboratory, and we simulate the conditions in a way which is shown here. So we cool down a substrate to 6K, deposit precursors, silicate precursors, carbonaceous precursors we have produced by laser ablation. We deposit them on a cold substrate together with a rare gas ice matrix. And we can do spectroscopy and define, let's say, the precursors and identify the precursors here in this first step. And then we apply a kind of trick, because we cannot wait millions of years. So we just simply anneal a little bit these ice layers, so by 2-3 kelvins, and then we trigger the diffusion of these species in the ice layers, and they can react between each other. And then you can see here, you can monitor these reactions in situ with spectroscopy, for example with infrared spectroscopy, and you can see the formation of silicates or carbonaceous material. And finally, of course, we can warm up and have a look on the materials in the final, in the electron microscope. And just very short, so we could see the formation of silicates. This is the in situ formation of SiO2. So you start with the molecules, you anneal a little bit, 2-3 Kelvin, then you start a diffusion. The molecular lines disappear and the silicate bands appear. So this is something for the simple system. It's also working for more complex silicates. You can produce everything: magnesium silicates, magnesium ion silicates, non-stoichiometric, stoichiometric. So the refractory materials we have identified are given here. So maybe it's not a complete list, but these are, let's say, the main contributors to the dust grain. And again here with the complex system, you see the appearance of a band already at 6.5K. So what I want to show finally is that the structure of the material is very, very similar to the high temperature material. So it's amorphous, made of small grains. They are already agglomerated, and this is a kind of low magnification image of these clusters. So you see they are very fluffy and these chain-like structures. So, okay, so, and this is a comparison to the interstellar silicate emission band, which was measured by GR and TLens 2006, and you can see it's a very nice agreement here with this interstellar emission band. This is not so important. Finally, we also produce something which, I mean, the real case is that we probably deposit refractory silicate materials and also carbonaceous materials. And the question is, what happens when we bring both species together? Do we produce silicon carbide, which we did not produce? We produce the separate phases, silicates and carbon again. But what also may happen is that you have reduction processes like formation of silicon grains or the formation of iron particles in these materials. Okay, this is my last slide, and I want to leave you with my summary, and thank you for your attention.
Measure the imaginary index at
you mean the mid-infrared spectra? Yeah, there are measurements of silicates at different temperatures, and the effect of the temperature in the mid-infrared range is not very high. So this has already been shown by Mutschke Henning et al. 1996, but this has also been reproduced by many others, Demuk et al., what I have shown 2017, yeah, and also by Koike and so on. Yeah, the effect is only at very long wavelengths, so let's say beyond 80 micrometer, then you see a clear effect on the absorption level and also, of course, on the slope of the curves. So
I have a question
yeah.
about the grain size distribution. Is that
Yeah.
something that's what can you tell us about grain size distributions as a function of the conditions, and is there a good understanding of under what conditions do you produce different sized grains?
At the moment, what we have seen from our, let's say, homogeneous condensation experiment is that we always produce, let's say, primary particles in a size distribution between, let's say, a few nanometers, let's say 5, 6 nanometers up to 15. So, and of course, the higher the pressure, the larger the grains, but it's still in the size range of nanometers. The effect is rather on, let's say, the agglomeration of the material. So they start to agglomerate and to form. Yeah, it's a little bit difficult to describe because you have primary particles, they agglomerate and form, let's say, intermediate agglomerates, and they agglomerate again and form these kind of big cluster structures I have finally shown. So, and of course, then you see exactly the influence of pressure. The agglomerates are getting denser, but still you see this kind of primary particle structure. So it's something. Hmm. uh, how we can uh, sorry, I didn't get your question. Yes, yes. You ask me for the, let's say, the origin of the distraction in a shock environment, or did I miss? Okay, when you have a shock wave running through the interstellar medium, then this shock wave accelerates atoms and ions, and they have, and also grains, and you get different velocities. Relative velocities are different for grains and ions and atoms. So that means finally you have processes like ion irradiation, and then sputtering, for example, plays a very important role. So if you are at low velocities, let's say lower than 300 kilometer per second, velocities of the shock wave, then you are exactly in the regime of very efficient sputtering, and then you can easily destroy small grains completely. Another process which destroys these particles are grain-grain collisions, so you have grain shattering processes which are also very efficient. So it's yeah, I mean, it's well known that, I mean, the numbers are not so clear so far. There are different models. I mean, the drain, for example, says about 90% of all the grains will be destroyed in the interstellar medium, but other people like Jones say, okay, it's only 50%. It's somewhere in between probably. And it's also different for silicates and carbon. Carbon, it's more easily destroyed in shock waves than silicates. Silicates are more resistant. Mm.
Thank you. Let's come again.
Mm.
next success with that one.
Okay, I'll just control it over here.
I think you have an
Yeah.
HDMI, right? Okay. 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 The color effects are not intrinsic, right?
I think it's
The
fine. It's just a little
I'm wondering if there's a yeah.
but I don't think it would be a big problem. It should be fine.
Okay. Okay. So the next talk will be given by Victoria Hartwick on meteoric smoke.
So hi everyone. So this is completely different than the last talk. So everyone just shift their brains a little bit. And it's also completely different from a lot of things we've been talking about this week. So I want you to think about our solar system, but also terrestrial bodies. So we're not talking about large gaseous planets anymore. So I'm going to be talking about a really unique process that happens to form these kind of what in the terrestrial community we'd call exotic cloud types. They're still water clouds, so not so exotic for most of you. But it's an exotic cloud type in the middle atmosphere of Mars, and I'm going to talk about the formation process for these. So based on the communications I've had with people at this coffee or during their coffee breaks, I felt like I needed to give you guys some photographic proof first. Yes, there are clouds on Mars. These are some really cool images from the various rovers, from Curiosity and Opportunity, looking straight up and actually seeing the clouds pass by overhead. So beyond just like the cool factor of seeing clouds from the surface of another planet, this actually gives us a lot of information about processes for cloud formation on terrestrial planets that are unique and should be considered because they have large-scale radiative influence that changes the large-scale climate. So we really need to consider these. So all of the types of cloud nucleation we've been talking about so far is homogeneous nucleation, which means it forms directly from the gas. The example we have is here, which is basically you have a bunch of small gas particles that conglomerate together. And this is actually really difficult, especially in terrestrial atmospheres, because the smaller and smaller you make these particles, the more the curvature increases, and therefore the more energy or the more energetic strain there is on those particles. So on Mars, to form a small water ice particle homogeneously requires supersaturations in excess of 100,000. So this is just not going to proceed easily in the Mars atmosphere, and this is pretty typical for terrestrial atmospheres in general. So we have clouds in terrestrial planets. How do they form? It's a process called heterogeneous nucleation, which basically you add a flattish surface, which often is a dust or biogenic material, and for the same number of particles, you really reduce that curvature. So now it's a lot easier to form that particle. The point is, now we have this new factor that we need to consider when we're looking at clouds and terrestrial bodies. So we have to keep track of what we call cloud condensation nuclei, or I'll call ice nuclei. And depending on the distribution and the properties of that, you can get very different cloud types. So one of the most common ice nuclei on Earth is mineral dust. And you all may have heard that Mars is really dusty and is actually still recovering from what the media like to call this monster dust storm that just covered the entire surface and killed the Opportunity rover. And this is really actually not that atypical for the Mars surface. The language is super hyperbolic, but Mars is really dusty. So cloud formation seems like a pretty open and shut case. We need ice nuclei, but there's an abundant source of dust from the surface. And for most of the planet, this actually works really well. This is one of many extinction profiles from the SpeakCam instrument, looking at extinction versus altitude. And what you'll see when we're close to the surface, from about 10 to 30 kilometers, the extinction falls off with altitude, this is the dusty mixed layer. And often you'll see right on top of that a cloud that forms exactly where the atmosphere is first supersaturated with respect to ice. But dust isn't actually very efficiently mixed beyond that altitude, and we still see these secondary cloud layers. So if that's the case, and we know we need ice nuclei, how are we forming these clouds? And I'll tell you, there is a bunch of really creative ways to loft dust to these altitudes. I have some concerns about many of them. I don't have time to go into it, but if you're interested to come find me, I'm going to talk about an idea we actually stole from the Earth community, which is in very cold, very aerosol-poor regions of Earth's atmosphere, we actually form clouds by condensing water vapor onto something called meteoric smoke, which is the burnt-up byproducts of maybe some of the dust that was discussed in the previous presentation, but I'm also realizing we use dust a little too liberally, so I'm even using it in 2 different ways in this same presentation, so sorry. So what is this interplanetary dust? So all of the planets are embedded in this dusty debris disk. Some of that material is primordial. Much of it is made by collisions between asteroids or outgassing from comets. And when it impinges on an atmosphere, it'll burn up. If it's really large, you get these beautiful shooting stars. But most of the material is actually really small, on the order of a couple of microns. When that burns up in our atmosphere, which it does, we don't see it with our eyes, but we do see these ionized metallic layers. And all that's happening here is you have a small particle entering the top of your atmosphere. As it moves through the atmosphere, it heats up. Really volatile elements burn off first. You get like a potassium and sodium layers. And then as it continues to move through the atmosphere, it burns off more, and we get these more refractive ionic layers, so like magnesium and iron. And we've actually observed this process happening on Mars with the NGIMS instrument on MAVEN. So this isn't altitude anymore, this is ion density versus time. We have those same ions, magnesium plus, sorry about the box, sodium and iron. And the point here is that we just, over a long period of time, we have a persistent ionic layer, which means meteorite ablation is happening all the time. So if we're lucky, we have a source of ice nuclei high in our atmosphere. And this is actually what's happening as those particles hit the top of our atmosphere. So we've used really, Plain et al. In 2018 developed a chemical model to simulate this process and created this. If you're like me and panic when you see this type of chemistry model, I'll try to simplify it. These here are the direct byproducts of ablation. Then, because Mars' atmosphere is CO2, we have this really unique chemistry or chemical pathways. The only one that's really interesting is directly down, where you hook magnesium up with carbonate, and then it grabs a bunch of water particles. This is what they call dirty ice. And this is a really good ice nuclei, especially at high altitudes where the temperatures are below about 180 Kelvin. So what I've done is input his results about the size distribution of this dirty ice. So here is the size distribution versus altitude. I took the model top of my GCM, and I take all of that and use it as an input at the top of my atmosphere. And just briefly, you'll see that about 80% of that total mass, which is 0.4 tons per day, is in the smallest radius bin, which is about 0.001 micron. I don't think I have time to go into how the model works, but it is acting as an ice nuclei, and it's a sectional model, so I'm not making a priori assumptions about the size. But let's just talk about results. So, first off, does adding these actually translate to an increase in the number of ice nuclei high in the atmosphere? Short answer is yes, and by a lot. So this is dust number density versus pressure. The dashed lines are simulations without interplanetary dust particles. Solid lines are with. So now we have this huge increase in the population of ice nuclei high in the atmosphere. And these do create cloud particles. So before, the number of cloud particles fell off with altitude. Now, in simulations with interplanetary dust particles, we have a new peak at about 10 pascals, which is exactly where we observed those cloud decks. We can also take a broader view. This is the zonally averaged extinction versus latitude and pressure. Here's simulations without interplanetary dust, with, and by comparison with MCS observations. And just by eye, it looks a little bit better, but we make improvements on the altitude of the peak of the lower cloud deck. What I think is more interesting is we also really improve the cloud altitudes at these lower pressures, so at about 20 pascals. And we're putting them also in the right spot. So you don't really have any clouds at this like 50 to 40 degrees latitude. And now we have that same one in both observations. So before I wrap up, I just want to tell you why you might care about this type of cloud. Unfortunately, clouds don't just passively trace through the atmosphere. They have radiative impacts that change the temperature structure of your atmosphere. So again, here we have those observations versus the two simulations. And you'll see that with interplanetary dust, these new high altitude clouds really warm the high atmosphere. And on Mars, this can have broad changes to your circulation that would impact dust lifting on the ground. So this can change huge climate and meteorological systems on the surface of Mars. And so just to place it finally in an exoplanetary context, all of these planets have zodiacal clouds or these dusty disks. Depending on the age, it might be dustier. Depending where you are in the system, you might be getting a higher flux at the top of your atmosphere. So when we start looking at spectrum of these terrestrial planets, and especially getting annoyed by those higher altitude cloud features, some of these might be forming on interplanetary dust grains. So it's something to consider. And I guess my biggest takeaway is, unfortunately, with terrestrial planets, we have to really start thinking about how the clouds form and thinking about what types of cloud condensation nuclei might be available. So I will put up my summary, and if I have time for questions, I'll take some. He's actually now adapted it to Mars, so he's collaborated with the MAVEN team to look at the unique chemistry that happens high in the Martian atmosphere. Depending on the environment at those altitudes, you could get more cloud formation or larger grains. There's some pretty interesting feedbacks when you actually do heterogeneous nucleation on the number versus the vapor available that can change the types of clouds and how quickly they sediment. So unfortunately, there's not like a really easy answer for that, but it is something we played around with. I'm not sure. I would imagine that it might be compositionally similar because the moons of Mars are just captured asteroidal material. But the processing of it might be different. I haven't thought about that.
So I think in coming years or decades, we will have a lot of measurement of zodiac
Mm-hmm.
around nearby stars.
Yeah.
Do you think we can start to draw correlation between those measurements and how cloudy the
I'd love to say yes. I think depending on where you are in the disk, you'll have a higher flux of material. So that's one thing to conclude. But for example, Earth has a much higher fluence. It's like 40,000 tons per day versus 0.4. But because it has so many aerosols just everywhere, and at where clouds form, you don't really see the influence of the meteoric material until you're in these really cold polar regions. So I think it would depend on the dynamics of the atmosphere and the type of atmosphere you have.
Let's thank Victoria again.
Yeah, good morning, everybody. Yeah, we're staying a little bit at Mars, but not present-day Mars, but early-day Mars, early Mars. So with early Mars, I mean Mars like 3.5 billion years ago. And the focus of my talk is actually not so much the climate of early Mars, but the challenges in the radiative transfer. Because we heard a lot of talks this week that clouds are important, so the formation of clouds is important, but I will show what problems can arise if you take a too primitive radiative transfer scheme that might change the outcome of your climate simulations. Yeah, this artistic impression of Mars here is probably not what early Mars looked like, so probably we didn't have these big oceans. But we know that from geomorphic evidence that there was liquid water on early Mars, maybe episodic. So for example, we have some riverbeds, some former lake structures. But actually from an atmospheric side of view, it's actually very hard to explain. Because present-day Mars has an atmospheric pressure of like 6 millibars, which is definitely not enough to have liquid water. We would need about 5 bars of CO2 to make the present-day Mars habitable. But the early Mars actually had a bigger problem. It had a faint young sun. And the faint young sun simply is the effect that the luminosity of the sun evolves over time. So this is shown here. So this is the luminosity of the sun in solar luminosities. This is billion years before present. So we are here with one solar luminosity. And if we go back to early Mars, we see that the sun only had 75% of present-day luminosity. So in fact, to make the early Mars habitable, we would need a substantial CO2 atmosphere, like 10 bars and even more. The problem is, if early Mars would have had such a dense atmosphere, we would still see some remains of that today. So not 6 millibars, but definitely a thicker atmosphere. But then again, maybe CO2 clouds could help us, because we know that clouds can have a greenhouse effect, as Anthony showed us, as Vicky showed us as well. So maybe CO2 ice clouds can help us, because it's a CO2 dominated atmosphere, it's cold, so CO2 can condense and form clouds. So the first thing we can look at are the optical properties of some CO2 ice particles. What is shown here is the single scattering albedo for different particle size distributions with several different effective radii. And what you can see is that from the visible all the way up to the far infrared, these CO2 ice particles have a single scattering albedo of almost unity, which means they simply just scatter radiation. They don't like to absorb infrared radiation or visible radiation, except for these small bands here. And this actually led James Casting to the conclusion, when he wrote his famous paper about early Mars, that since there's no absorption and emission of infrared radiation, the clouds will just cool the surface of early Mars. So he didn't think about any like scattering processes. 6 years later, there was this very famous paper by François Forget and Ray Pierre-Humbert, where they actually looked at the scattering properties of the CO2 ice cloud particles. And the way it works is shown on the right-hand side here. So as Anthony and Vicky showed us in her talk, clouds always have two different kind of climatic impacts. They have the albedo effect at short wavelengths and maybe greenhouse effect at longer wavelengths. So at shorter wavelengths, we have like the solar insolation. It hits the cloud, some of it is reflected back to space, some of it is transmitted, and then the cloud base and the atmosphere and the surface kind of play ping pong with those photons until they finally either absorb down here or transmitted through the cloud base. The other thing you can have in the infrared, of course, you have upwelling infrared radiation. Some of it is transmitted to space, and some of it can be, in case of CO2 clouds, can be reflected down to the surface, which creates a greenhouse effect. And depending which of these two effects wins, the cloud either heats or cools the surface. What François Forget and Ray Pierre-Humbert did, they simply used the model from James Casting. They put in the CO2 clouds for like two different cloud particles, 10 micron, 50 micron particles, and they looked what kind of climatic impact they had. And so this is the surface temperature as a function of the optical depth of the cloud. And as you can see, if you go to zero optical depth, so the cloud-free case is about 230 Kelvin. So definitely it's not habitable, so no liquid water. But as you increase the cloud optical depths, you see that the greenhouse effect actually wins over the albedo effect. And above a certain optical depth, you actually are above the freezing point of water. Especially if you like 50 micron particles, if you go to an optical depth of like 20, the resulting surface temperature that you get is larger than 300 Kelvin. This is actually larger than present day Earth, for example. So they estimated that CO2 clouds can very easily warm up the early Mars, and that the outer boundary of the habitable zone is located at 2.5 AU, so far above the present-day orbit of Mars. The problem is that what they did in their climate simulations is what most of the actually climate models do. They use two-stream approximations in their radiative transfer schemes. So in particular, for the experts in the room, they use a delta Eddington for shortwave radiation and a so-called hemispheric mean two-stream in the infrared. Two-stream approximations, the name actually says it, they only account for like two different directions. So they only account for an upward direction and a downward direction of the photons. But of course, photons don't just travel up and down, they travel in all kind of different directions. And this is actually important if you have scattering by large aerosols. So what I did in 2014, I came back to this important effect, and I did a simple estimate on the scattering properties of CO2 ice clouds. So I basically just took a cloud layer, so no atmospheric model, just a cloud layer. I used the 24-stream radiative transfer method. That means instead of just up and down, I had like 12 angles in the upward direction, 12 angles in the downward direction. And then I just simply looked how much is transmitted through the cloud layer in the optical and how much infrared radiation I can reflect down. And what I found is that the two-stream methods like overestimate the scattering by 20% in flux. So it's like a 20% change in flux, which is actually quite enormous. The problem is, at this point, I couldn't study the impact on the temperatures because all the atmospheric models that were available to me, well, they used, of course, the two streams because that's what people use for planetary atmospheres. So I built my own model that uses very high order discrete ordered methods. And I revisited this effect. So I basically took my atmospheric model, took the same assumptions that Ray Puhamrit and François Forget did, and redid the calculations. And this is, Vicky already showed this. So this is what you get. So this here is the change of temperature, of surface temperature, if you have the cloud as a function of optical depth. And you can see this is the original result from Forget and Puhamrit. If the lines are getting thicker, that means that we have reached the freezing point of water. So everything above here is like liquid water on the surface. But as you can see, the simulations with a detailed radiative transfer actually never reached that point. They have a maximum effect around an optical depth of 8, and then they just decrease because at one point the optical depth of the cloud is so high that you just reflect all the solar radiation back to space, and then your greenhouse effect can't do much. The biggest effect you see at like an optical depth of 20. So if you compare like these two results, it's like a difference of like 60 Kelvin in surface temperature. And for a planetary atmosphere, this is actually quite a lot, just by changing the radiative transfer scheme to get a difference like 60 Kelvin. Well, then I thought, because Ray and François just looked at two different particle sizes, maybe there are other particle sizes that might be more effective. So I actually varied the particle size here from 10 microns all the way up to 1000. This is the optical depth from 1 to 20, and this is the resulting surface temperature. And you can see there's a kind of a maximum. And if you look down here, then the maximum, so the most effective particle size for the scattering greenhouse effect is about 25 micron particles at an optical depth of 8. But even those particles only give you surface temperature of early Mars of like 250 Kelvin. So it's definitely not enough to warm up early Mars above the freezing point of water. But still, this effect might still be important because at the outer boundary of the habitable zone, as Vicky told us, you need basically every Kelvin of greenhouse effect that you can get. And the change in from clear sky to like this maximum here is around 30 Kelvin, and 30 Kelvin is quite a lot. That could still push out the outer boundary of the habitable zone. Yeah, so the take-home message for early Mars is that the CO2 clouds alone cannot provide enough heating to warm up early Mars, but they may still be important for the outer boundary of the habitable zone, and that two-stream methods basically strongly overestimate the cloud forcing. So you should be, if you use two-stream methods, you should be aware of the limitations they have, because as Mark told us on Tuesday, they come in very different flavors, and each of those flavors has different assumptions. They were made for like different scenarios, and you have to know what kind of scenario they have been made for. That means if you have your most favorite two-stream code, you should test the models before applying them to new scenarios. So for example, what Ray and François Forget did, they just took an Earth model and applied it to a situation that was not made for. Fortunately, in Bern, we have been working on improving those two-stream methods by 2 papers led by Kevin Heng. We are actually trying to improve the two-stream methods by introducing like artificial correction factors that make them such that they yield the same result as a high-order discrete ordered method. Okay, yes, that's it. Yes.
Yeah, so I assume that your best case scenario with 250 Kelvin is an annual planetary average.
Yes.
So do you have any idea, because maybe at some seasons, some times of day, at some locations on Mars, isn't that far away, right, from 250? So
Yeah, but it's still 20 Kelvin, and you have to tune the particle size very correctly. You have the right optical depths. I don't know if you could tune it that way.
yeah, but like modern day Mars, the temperature swings are like many tens of Kelvin.
Yeah, but this is because the atmosphere is only like 6 millibar. This was a 2 bar CO2 atmosphere.
2 bar. Okay.
Yes.
So then we have to do something to get Mars up to the
Something else other than CO2 clouds, yes.
So would you, let's say, subscribe to let's say, some of this recent stuff that Robin Wordsworth has done with H2, CO2, and methane?
And N2 probably as well. That it definitely pushes us in the right direction. The problem is that like the difference that you need in surface temperature is so big that, I don't know, that even a bit of methane or, I mean H2, but then you have to lose all the H2 over like 3.6 billion years, which might be possible, yeah.
So Brian Heineken and others showed that there are some kind of correlations between the volcanic activities and the temperature, presumably, the water content on the early Mars surface.
Mhm.
So do you think that would change if we add, for example, a volcanic, eruption to these models would change the outcome and we would get the warm early Mars?
Well, the problem with volcanic eruptions is that you also get a lot of aerosols. So they again scatter your sunlight away.
And also the composition would change, right?
Yes, you might put in more greenhouse gases, that's right, but you also might produce aerosols. So in the end, it's maybe a zero-sum game, who knows?
The Fortian Camber, it's all like 1D models, right?
Yes, it's all 1D model, yeah. Because the 3D models can't run like high-order
Yeah, no,
discrete
sure,
ordered
but
methods.
So it means that you're assuming that the cloud coverage of CO2 clouds is
Yes,
continuous.
yes.
Is that somehow realistic to
No,
produce your CO2?
but it
or
gives you
is
the-
gonna be patchy cloudy and so
They're
if you're
It will probably be patchy clouds, of course, because if you look at Earth, we always have patchy clouds. But like if you assume a 100% cloud cover, that gives you the maximum effect. So patchy clouds will just decrease the surface temperature. Yes. So it gets even worse. Yes. The the one that I use, the so-called dicehort code, I think for 100 layers and 4 streams, it's in the millisecond order for 1 column. So I'm not sure if that's feasible for like GCMs. That's Vivian. Okay. But yes, so 1 column is like in order of milliseconds.
I have a little bit more specific question about the plot that you showed. Can you please put that?
Which one?
The one where you compare the Fortier
This one.
with the model. Yeah. So I'm interested in the optical depths between until let's say 4,
Mm-hmm.
where you see the increase, and what kind of scattering processes are causing that.
You mean?
Yeah, the first increase and yeah.
I mean, first is as you increase the optical depth, you increase the scattering greenhouse effect. So that like increases your surface temperature. But at one point, if you increase the optical depths too high, too large, then the clouds will just scatter the sunlight out of the atmosphere. So that will like create a dominating cooling effect. It's like a balance between the albedo effect and the greenhouse effect that you see.
Does this change if you change the particle sizes?
Well, sorry.
Would the
you actually have to tune the particle sizes very well for this effect to work. So if you have very large particles, they tend to like forward scatter a lot, which is good in the optical because they scatter the radiation down to the surface. But if you have large particles in the infrared, they just scatter the infrared radiation upwards back to space. So you need to have the right particle size such that they are large enough in the visible and like almost Rayleigh scattering like in the infrared to make that thing work.